Welcome to Chemistry 111. Right now, we had previously talked about the first law of thermodynamics, basically stating that energy can neither be created nor destroyed, that it all has to come from somewhere. We cannot make energy from nothingness whole cloth. So what you have to do is look at the transference of energy. And where we're going to look at as the change in internal energy of a system. We look at, say, a reaction. Has energy left the system overall, or energy entered the system overall? Look at that by summing up all the terms of all the types of energy. All right. We will focus largely on two types of energy. Basically, work, small w, and heat, small q. Those are the two main types of energy. Kinetic energy is present, but in most cases, it's not significant that we need to consider that. Potential energy, we won't really worry about that. And electrical energy, well, that's for another chapter when we go back to talking about redox reactions again. But work and heat will cover most of the things we deal with in real life. It's on a chemical level. We look at gasoline. What does gasoline do to the engine? We insert gasoline in the engine, we ignite it, it burns. What does it do when it burns? It produces heat, hot gases that will come out the tailpipe in the end. But when it produces those hot gases, it will produce work, which is the gases will expand, they will push a piston, they'll turn a crank. That's going to essentially move our axle, move us forward. Going to do heat and work. When we look at work, what is work really? Work is a force applied over a distance. So, or kilogram meter squared per second squared to get us in joules. One thing to note is if a force doesn't move an object, there is no actual work done. So I could push against this whiteboard behind me all I wanted. If the board doesn't move, if the wall doesn't move, even if I'm sweating, no work is done. When we think about heat, what is heat? Heat is the transfer of energy from hot to cold. Cold is not really a thing. Cold is actually just the absence of heat. Just like vacuum is the absence of matter. You have a vacuum and you bring matter near it, matter is going to expand into that vacuum. If you have heat and you bring it near something that's cold, heat will expand to replace that coldness. So if the system is hotter, the surroundings will gain the heat. The system will lose it, so we'll see a negative Q if the heat leaves the system. And of course, if the system is colder, the surroundings will give up the heat, and so the system will gain it with a positive Q. So absorption of heat is positive, release of heat would be negative. So here's more likely than not how we'll see these problems. Putting it together, we'll look at the internal energy of a system as a sum of all the heat and the work. You'll be given two numbers and you'll add them together. But the difficulty is you'll have to determine what is the sign. Is this leaving the system or entering the system? And that's how this problem becomes even moderately difficult. But we're simply adding two numbers together. Just one of those numbers, or both of those numbers, could be a negative. So look at this. A particular engine absorbs 58 joules of heat when it produces 70 joules of work. So how would you characterize the internal energy of the system? So breaking it down. Heat, we say 58. Now, is it positive or negative 58? Well, is heat going into the system or out of the system? Well, it is absorbing heat. When it absorbs heat, it goes into the system, so it's a positive Q. Now the work, it's 70 joules. Now, is work done on the system, meaning it goes in, or is work done by the system, meaning it comes out? Well, this produces work. When it produces the work, it goes out. So we have a negative 70. At that point, to find the internal energy of that system, you would add the heat and the work. When you add the heat and the work, you get your change in internal energy is equal to negative 12 joules. Negative 12 joules. So I've just added those those numbers together, those two constants. So that's probably the main way you'll see this equation. One other thing we'll have to deal with, and this is a big thing for this chapter, is state functions. And this is one of the trickiest concepts. It's kind of really hard to see until we kind of like see it in action. But internal energy is a state function, meaning the route, for a state function, the route you take to get there does not matter, only the destination. So my starting point and my ending point does not matter, are the only two things that matter. If I'm here in the science building and I want to go to Chick-fil-A, it doesn't matter if I walk across campus cutting through the quad, or if I take a car and drive down the street, turn the corner, stop at the Velo, and then get there. It doesn't matter how I get there. It just matters, here's my beginning point, here's my ending point. The energy will always be the same. If you look at it on a destination, like empirical, when we look at that, one way is empirically shorter. I can go a more direct path. The other one maybe a little bit longer because I have to go over speed bumps, dodge students, find a parking spot. But the end result is the same. I've gone from here to there. There's a couple other state functions like this that we'll look at. On this chapter, we'll look at U and H. H is enthalpy. But we'll also look at state variables pressure, volume, and temperature. And next semester, we'll look at Gibbs free energy, delta G, delta S, which is entropy, more. All of these equations with a capital letter end up being state functions. Now, on the other way, heat and work, those are given as lowercase q, lowercase w. Those are not state functions. The work needed to get to Chick-fil-A will depend on the path I take. The work needed will depend on the path I'll take. In this case, I can actually use this. This might be a good example. So say it's cool out. So we'll say, well, actually, let's say it's warm out. The amount of energy it takes for me to walk there across campus is less than it would take to maybe drive there, because you have to burn a bunch of gasoline, find a parking spot. But all in all, the heat may be a little bit less if I drive, because, I can run the AC. I'm not going to be sweating when I get there. So for me, the work may be more to drive there, but I'm going to have less heat. So depending on what path I take, heat may go up, work may go down, but the change in energy is the same. The change in energy is the same. The idea that I could take a path that gives me 50 joules of heat, 50 joules of work, half and half, to give me 100 joule change. I could take another path that only gives me 20 joules of heat, but it would then have to give me 80 joules of work to give me a total change of 100. I could take a path that uses 70 joules of heat and thus would only produce 30 joules of work. So it's 100. The idea, depending on the path, the Q and the W will change, but the sum will stay the same. The energy released or the energy gained for the system will stay the same, the net sum. Now, this is why engineering is such an important field. You try to get the efficiency up. Efficiency is the key thing of why we have fuel economy. We're trying to make an engine burn more cleanly and get the most amount of energy. There's a set amount of energy in gasoline. When we burn gasoline, we want to get as much work as possible from that gasoline. But when we lose heat energy, the work we can get goes down, which is why heat drain is a big loss of efficiency. We can't get as much work, which also is why diesel engines are so much higher fuel economy. They experience a lot less heat drain. So they get a lot higher efficiency when they burn the gasoline or when they burn the diesel. They can get more work out of the same mass. You can get more work out of the same ignition. So you get a much higher fuel economy. If we could get a system that produces 100% work and 0% heat, we get like incredibly high fuel economy. In fact, many electric vehicles, when you do electricity, oftentimes you get the highest fuel efficiency possible. The only problem right now is electric vehicles have certain problems, like you need very rare minerals to do that, and sometimes toxic processing to get that. So right now we need to make cheaper batteries to get, so we can get everyone in electric cars. Okay. So going back to state function, the main state function we'll look at for the majority of this chapter is actually enthalpy. It's the state function we'll use for most reactions. Enthalpy is the heat exchange process at a constant pressure. So I am essentially saying, how does heat flow when we keep the external pressure constant, which in all intents and purposes means we allow this to react in an open vessel. I put two chemicals together in a beaker on the table and let them react. How does the heat flow under those conditions? I could put this in a constant volume. I could put them in a sealed box, but that would be a different setup. But as long as we're doing it in an open beaker, the external pressure, which is the pressure everyone is feeling right now, is more or less constant. And so we can measure the heat flow under those conditions. And this is much more useful than Q. In most reactions, because essentially most reactions occur open to air. Now, considering work done at a constant pressure. Work pressure is force applied over an area. And if work is force times distance, we can say work at a constant pressure is a force divided by an area times the volume, because area times the distance would be volume. And essentially we can say that work done under constant pressure is equal to negative pressure times the change in volume. The negative sign is there to make sure that the negative work has to do with expanding gases. It's trying to get the sign of work the same. So now our delta U, instead of being Q and W, can be delta U equals delta H minus P delta V. This is looking at that same equation, all under state function conditions. Now, this thing is essentially modeling an explosion. Because what is an explosion? An explosion is the production of gratuitous amounts of heat, or enthalpy, and a rapid expansion of gases against the external pressure. It explodes outwards, pushing something with it. Now, the measurement of an energy of explosion will be the quantification of this heat that is produced and what degree of expansion we have. Cars are the most common type of explosion. That explosion will turn an eccentric motor. But, a grenade. What's a grenade do? It explodes. You have some fuel source in there. It ignites, produces a bunch of heat, and the gases expand until it pushes out on the grenade, and the grenade shatters, shooting fragments everywhere. In fact, some fragmentation grenades, they have tiny little BBs in there that essentially when the gases expand, they push the BBs everywhere, and essentially they all scatter in every direction. But the idea is just basic. Gases expand, producing a lot of heat, creating this shock wave that shoves everything backwards. Okay, now I'm going to go ahead and go through this practice, but I'm pretty much told the other class, and I'll tell you, we're less likely to actually use this equation on a test. This one is a little bit more tedious. There's a couple more steps involved, and it will trip up most people. But I'm going to go ahead and rewrite the equation, and then I'll switch to the screen. So delta U equals delta H P delta V. They say delta H, we say, what would the internal energy of a system, a gas that absorbs 123 kilojoules of heat and allowing it to expand, so a change in volume of 58.94 liters under external pressure of 3 atmospheres. 1.3. Okay. Now, the reason I'm going ahead and showing you this, despite the fact that I know I'm not going to test over it, is because it's a good test of understanding units and why and how we deal with units. Okay. H is already given. We don't have to do anything with the H. We have to, however, calculate the work. The work is our negative P, so 3 ATM times our change in volume, which is 58.94 liters. Atmospheres and liters do not cancel out, so the unit we would get is a ATML. ATML, atmosphere liter. So doing that seems pretty straightforward. 3 times 58.94. We'd get the work function, the negative P delta V is equal to negative 176.82 ATML. So do I just add that to 123? The answer is no. Why? Because atmosphere liters are a different unit than a kilojoule. We cannot add a centimeter to a meter and expect the math to work out fine. We cannot add a centimeter to an inch and expect the math to work out fine. We have to convert until we're both in the same unit, which is why we have an atmosphere liter is equal to 101.3 joules. But furthermore, there is 1,000 joules in 1 kilojoule. 1,000 joules in 1 kilojoule. So we're going to take that 176.82 times 101.3 divided by 1,000. So we get the work actually done is negative 17.9 kilojoules. So adding that back in, we have positive 123 minus 17.9. We see a change in 105.1 kilojoules. As I said, that is a lot more tedious. I'm less likely to actually do something like that on the test. However, I wanted to show you that for the sake of showing you the concept. We have to make sure the units are the same before we add anything together. We cannot add apples to oranges and expect to know how many apples we have. We can, if they're in the same unit of fruit, we can add them together. Okay. Okay. Now, we've all been through the lab. We did the titration lab, or at least most of us have. Next week lab has to do with calorimetry, which is going to be our big concept here. The first thing we need to consider when we deal with thermochemistry is that heat flow will heat an object up. The study of this heat flow into objects is called calorimetry. Now, every object will warm up or cool down based on different amounts of energy. You ever notice that metal heats up very rapidly? It doesn't take much energy to heat up some metal. It's easy to burn yourself on metal. Organic liquids and water are actually rather difficult to heat up. It takes a lot of energy to boil water. A lot of energy. The specific heat capacity is the measure of this. The specific heat capacity, capital C, is given as joules needed to warm up 1 gram of an object 1 degree Kelvin or 1 degree Celsius. It doesn't matter whether you're looking at Celsius or Kelvin, the result will be the same. But it has to be Celsius or Kelvin. You can also measure this as joules per mole Kelvin, but we're more likely than not looking at this joules per gram of the object Kelvin. So the unit is going to be J per GK, which is going to fit right into our equation. I will give you this equation when you need it, but the fact of the matter, this equation is pretty easy to remember. Q equals MCAT. For those in pre-med, you all know your MCATs. But Q equals MCAT. Q, our heat, is equal to the mass times the specific heat capacity, C, times our delta T, how much temperature is changing. If C measures the energy needed to heat up 1 gram, 1 degree Kelvin, or 1 degree C, we need to take into account how many grams do we actually need to heat up. And then we need to figure out how many degrees are we going to heat that object up. And so we will deal with Q equals MCAT and to calculate how much heat is required to do this. So let's look at this in practice. So first, how much energy is required to heat up 4 liters of water from 25 to 100? And then how much energy is required to heat up 5 kilograms of tin from 25 to 170? So, standard equation. Let's write down what we know. So, our equation, Q equals MCAT. For our water, the mass of water is 4 liters, which is not a mass, but we have the density. There is 1,000 milliliters in 1 liter, and there is 1 gram per 1 milliliter. So we have 4,000 grams. Our specific heat capacity of water is 4.184 joules per gram Kelvin. And our delta T is going to be our T final minus T initial. So 100 minus 25, 75. And if I do the same for our tin, I'm going to do the same for our tin. The mass of our tin is going to be 5 kilograms, which is 5,000 grams, because there in 1 kilogram there is 1,000 grams. Our specific heat of tin is 0.22 joules per gram Kelvin. And our delta T, which is our T final minus T initial, 170 minus 25, be 145. Now, real quick, doesn't matter whether this is Celsius or Kelvin. No. If I do this, the water, if I do the water in Kelvin, I'd have 298, or I'd have 373 minus 298. That would still give you 75. Okay. So let's look at this. So we have our 3 numbers. Boom, boom, boom. At this point, it's just multiplication. So 4,000 grams times 4.184 joules per gram Celsius, or joules per gram Kelvin, times 75 degrees Celsius. Celsius and Celsius cancel out. Grams and grams cancel out. We would get an energy in joules. Doing this real quick, we get 4,000 times 4.184 times 75. We get a really big number, but that's because that's in joules. But even if we turn this into kilojoules by dividing by 1,000, we still get a really big number. We'd get 1,255 kilojoules. I've just divided my answer by 1,000. Otherwise, we would have got 1,255,200 joules. It's okay to get a big number. You're heating 4 liters of water up to boiling. That takes a lot of energy. You ever try to boil a pot of water for spaghetti? It takes a while because you have to pump a lot of heat into that to get it there. So let's look at tin. We're heating more tin to a higher temperature. But you'll see something. More tin to a higher temperature, but 145, okay. Boom, 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 boom. 5,000 times 145, but times 0.22. And I'm going to divide by 1,000 to get this into kilojoules. You would have 159.5 kilojoules, or 159,500 joules. So I'm heating 1 kilogram more of tin, almost twice the temperature, but yet it's almost 9 or 10 times less energy. That has to do with metal has a really low heat capacity and water has an incredibly high heat capacity. Okay. Now, how will we actually measure calorimetry? We're going to do this using a calorimeter. I know, really complicated name. We measure calorimetry with a calorimeter. But it's going to rely on the concept of the first law of thermodynamics. That energy is conserved. the Q of the universe is 0. With that being stated, the sum of the heat of reaction plus the sum of the heat of the solution is going to add up to 0, which is why we can, if we flip them around and separate them, set them equal to 0 and separate them, we could say the heat gained by a solution is equal to the negative heat of a reaction. The negative heat of a reaction. So we're going to let a reaction occur on a substance, and then we're going to measure the temperature change that occurs in the surroundings. And if we measure the temperature change in the surroundings, we can know how much energy was in that reaction. We're going to take the basic concept of Q equals MCAT and apply that here. We're going to apply this here. We're going to measure the heat change in the surroundings. Now, there's two types of calorimeters. We are going to use the constant pressure calorimeter. But the calorimeter is used to measure you could use it to measure the specific heat of a solid, or you can measure the delta H of a solid with the constant pressure one. So it's an open reaction vessel, open to the atmosphere, such as a covered coffee cup, which is what we're going to use. There's fancy ones, but we're going to just use covered coffee cup with water. If the hot substance is dumped into the cup or a solid is dissolved into the water, the temperature will change, and we can measure that temperature change of the water. So if I put a hot object into there, Q equals MCAT for the object is going to equal Q equals MCAT for the water. So if I measure the heat flow into the water, I can measure the heat flow from the solid. If I can measure the heat flow from the solid, I can figure out what that is. Is this steel? Is this aluminum? Is this brass? Is this gold? Based on the heat capacity of that solid. They all have different numbers. But if I dissolve something, I could just essentially look at, if I know how many moles are there, does the water heat up or slow to cool down? If I mix acid into water, it's going to heat up. It's going to heat up a lot. If I mix a salt, certain salts like potassium iodide, the water is actually going to get chilly, downright icy cold, because as the salt dissolves, it needs energy to break those salt bonds. And so you can look at how much energy does it take to dissolve this. Now, the other one is a constant volume calorimeter, also referred to as a bomb calorimeter. It's essentially an enclosed box. You have the substance in there, you burn it, you explode it in that box, and the box is surrounded by water. The water surrounding the box will heat up or cool down based on how much energy is produced into that box. And in this way, you can measure the internal energy of that object. So, however, in all these guys, we have to account for the calorimeter, because the calorimeter would technically heat up a bit. But this bomb calorimeter, this is essentially how you would calculate how many calories are in this food you're eating. You send it to this specialized thermochemist. You would essentially put this in here, burn it, and figure out how much energy do you get when you completely consume this object. And then we can apply that. Well, if this is how much energy we'd get when we completely burned it, this is how much energy you would get if you completely ate it. And so that's how we're going to figure this out. We're going to use this as a method to find out how many calories are present within this object. So, okay. So this is a practice. This is somewhat similar to what we'll do in lab. You'll mix, I have these hot iron balls. I'm going to take 50 grams of them, heat them up to 100 degrees. I'm going to drop them into 10 mils of water and the temperature of water at 25. The water heats up to 5121. So what is the specific heat capacity of iron, assuming that the calorimeter does not lose any heat? So let's set this up and solve this. So we're going to set that the Q of the water equals negative Q of the iron. So negative mass of iron times specific heat of iron times delta T of iron equals mass of water, C of water, delta T of water. Let's write down all we know before I flip it over. We have mass of iron, it's 50. We have T initial of iron is 100. We have mass of water, it's 10. We have T initial of water is 25. And we're going to say the specific heat of water is 4.184. Finally, the T final is 5121. Okay, with that in mind, so we can calculate the heat of water just fine. So we're going to have 10 times 4.184 times 5121 minus 25, or essentially 2621. So the heat of water is going to be how many joules? How many joules did the water absorb? 10 times 4.184 times 26. It absorbed 1096.6264. Okay. Now we're solving for C of iron. So I'm going to divide both sides by the negative mass, so negative 50, and divide by our delta T. And here might be the tricky part. So what is our final temperature of the iron? You might think we're not given enough information here. But the final temperature of the iron is actually the final temperature of the water as well. When the iron cools down, it cools down to the same temperature of the water. If they were different, more heat would need to flow. They're going to reach the same temperature at the end. So 5121 minus 100. That negative sign may be throwing you for a loop, but that negative sign is able to take care of that negative temperature. The negative sign is able to take care of that negative temperature. So that's actually what, like negative 48.79. So we have our 1096.6264 divided by 50 divided by 48.79. A negative and a negative make a positive. We get that the specific heat of iron would be 0.450 or 4495 joules per gram Celsius or joules per gram Kelvin. But that is a common thing. You could do this and find out what is your metal. Is this pure iron? Is this pure silver? Is this pure gold? Because pure gold is going to have one specific heat capacity. Some amalgam, something that isn't pure is obviously not going to have the same heat capacity. It's going to have some mixed heat capacity. So that is a standard type problem. Where we're going to take this has to do with enthalpy of reactions. Now, all reactions will have a certain energy change associated with them, either whether they're absorbing energy from the surroundings or releasing energy to the surroundings. But there's going to be energy associated with this. And these energy values can be determined by calorimetry as well. But every balanced reaction, whether it's a simple reaction or a complex reaction, can be described with a delta H, or enthalpy of reaction value, that Rx reaction. So if I burn hydrogen and oxygen gas to make water, I would get negative 483.6 kilojoules per reaction. I do this, I would get that much energy every time I run 1 mole of this reaction. Every time 1 mole of oxygen burns, I would get that much energy. I take this reaction from last chapter. Iron oxide plus carbon plus O2, iron and CO2. Take the energy associated with those. This would net produce 716.68 kilojoules of energy to do this. Even though it takes energy to start it, it ends up producing more energy to keep it going. Now, enthalpy is an extensive property, meaning the amount of heat will depend on the amount of molecules you use, which is a good thing. So if I use 2 hydrogens, I get 483. If I use 4 hydrogens, I get 967. So if my room isn't hot enough, I throw another wood onto the fireplace, another log onto the fireplace. If I need to heat up the grill even more, I throw some more charcoal onto there. It produces more energy when I do that. So I can produce higher heats. And because of this, there's also something associated with this, that if you can calculate the forward reaction, you can also calculate the reverse reaction. And so the energy associated with the reverse reaction is going to have the opposite sign. Basically saying, if it takes 483 kilojoules, if you produce 483 kilojoules to burn hydrogen gas and get water, you would take 483 kilojoules to split water back into hydrogen gas. And this is one of the main reasons hydrogen fuel cars are not readily available. We have to, one, be able to produce hydrogen gas cheaply. Right now, if we want to produce a bunch of hydrogen gas, we have to, like, say, split water out of like a coal-powered plant, or like a gasoline-powered plant, a diesel plant, something that's going to burn and pollute to get the energy to split this apart. We find a nice solar plant that does this, then we can maybe cheaply and cleanly produce our hydrogen gas. Otherwise, we're just polluting somewhere else. 2, we got to find a way to store it and get it back out very efficiently. And 3, we have to idiot-proof it so someone's not smoking at a gas station and then accidentally blows up the whole gas station because you have a leak of hydrogen gas. So there's a couple problems we got to work on, but it's coming. It's coming. But we're going to look at enthalpy of reactions for a whole manner of situations. We can look at enthalpy of the reaction, as I said, but we can also look at enthalpy of solvation. How much energy is associated with dissolving this? We can look at enthalpy of vaporization. How much energy is associated with boiling this? Enthalpy of fusion. How much energy is associated with melting this? Because we could look at the reaction of solid metal goes to liquid metal, or solid ice goes to liquid ice. How much energy is associated? There is an energy associated with everything. Now, because enthalpy is a state function, enthalpy only depends on the products of the reactants of the balanced chemical reaction. this is why this is so important. Enthalpy doesn't depend on the reactions you need to get to those products. It just cares about the final products and the final reactants. This is where you can really see a state function right here. So we could look at burning hydrogen gas to get to steam. This has set energy. We said 483. But we could also look at how much energy is associated burning hydrogen gas to get to liquid water. That is going to be a different energy. And then add on how much energy it would take to boil the water to get it to steam. So the net result would be steam, gaseous water. It doesn't matter that I had to do 2 steps. If I add step 1 and step 2 together, I would get the same answer as if I had just gone straight to steam from the get-go. Look at this. This is a basic reaction. I burn carbon with oxygen gas to get carbon dioxide. You throw coal on the fire, you get energy. This has a set energy associated with this. But a side reaction that often occurs, which is less good, which is why we tell people not to hibachi in the dorm, is it produces carbon monoxide. You can produce some carbon monoxide from the incomplete combustion of coal or charcoal. Carbon monoxide is kind of deadly. And so we don't want people cooking indoors. Now, this has less energy associated with the incomplete combustion. However, a good coal power plant can collect that carbon monoxide and reuse it. They collect it and continue burning it, and they get CO2. So they take care of the toxic byproduct and produce the benign but, still climate unfriendly product. But if you add step 1 and step 2 together, 1 carbon plus a half oxygen plus another half oxygen equals a whole oxygen. 1 carbon plus 1 oxygen, those are the same starting materials. CO2 is the end product. CO2 is the end product. If you add step 1 and step 2 together, you would get the original complete combustion energy. And that is what it means to be state function. It doesn't matter if I do 2-step reaction or 1-step reaction, you would get the exact same energy as long as you have the same starting product and the same ending product. Well, that's all the time we have for today. We did very good. Nothing crashed. I'm happy. So I'd like to thank you for your time. If you need me, I'll hang around for a few minutes. But otherwise, have a good day. Have a good weekend. Don't forget, homework is due this weekend.